In this episode of Cloud AI Adventures, find out how to train on increasingly complex datasets by converting a linear model to a deep neural network. As the number of feature columns in a linear model grows, it can be increasingly difficult to achieve high accuracies in your training, as the interactions between different columns get more complex. This is a known problem, and one particularly effective solution for data scientists to use is deep neural networks. Deep neural networks are able to adapt to more complex datasets and better generalize to previously unseen data because of its multiple layers, hence why they're called deep. These layers allow them to fit more complex datasets than linear models can. However, the trade-off is that the model will generally tend to take longer to train, be larger in size, and have less interpretability. So why would anyone want to use it? Because it can lead to higher final accuracies on this complicated dataset. One of the tricky things about deep learning is that getting all the parameters to be just right can be very tough. Depending on your dataset, the configurations can seem virtually limitless. However, TensorFlow's built-in deep classifier and deep regressor classes supply a reasonable set of defaults that you can get started with right away, allowing you to get going quickly and easily. Let's see an example of how to update our iris example from a linear model to a deep neural network, often abbreviated as DNN. Now, we don't have time in this video to properly show off a 2,000 column model that a DNN would leverage, so I'm just going to use the 4 that we've been using throughout this series. The main change comes from replacing our linear classifier class with DNN classifier. This will create a deep neural network for us. Virtually everything else remains the same. There is one additional parameter that is required for the deep neural network that we did not include previously. Since deep neural networks have multiple layers and each layer has potentially a different number of nodes, we'll add a hidden units argument. The hidden units argument allows you to supply an array with the number of nodes for each layer. This allows you to create a neural network simply by considering its size and shape, rather than writing the whole thing from scratch by hand and wiring everything up. Adding or removing layers is as simple as adding or removing an element in the array. Of course, with any pre-constructed system, what you gain in convenience, you often lose in customizability. DNN classifier tries to get around this by including a number of additional parameters that you can optionally use. When left out, some reasonable defaults are utilized. For example, the optimizer, the activation function, and dropout ratios are all available to customize, along with many others. What else do you have to do in order to convert our model from linear to deep? Nothing. That's the beauty of using the Estimators framework. One common way to organize your data, training, evaluation, and model exporting, while still giving you the flexibility to experiment with different models and different parameters. Sometimes, deep neural networks can outperform linear models. In these situations, TensorFlow makes it easy to switch from a linear model to a deep one with very little code changes by leveraging the Estimators framework to replace just one function call. This means more time to work on the data, model, and parameters, rather than wiring up your training loop. I'm Yufeng Guo, and if you want to learn more, be sure to subscribe to the channel and check out the rest of Cloud AI Adventures. Don't forget to use TensorFlow Estimators for easy, deep neural networks. Thanks for watching that episode of Cloud AI Adventures. You can catch the whole series here, and if you have any thoughts and comments, feel free to leave them down below.